Hello everyone. Today we're going to be learning about NOR and NAND gates. So on the left hand side we have a NOR gate, which is essentially just an OR gate with an inverter attached to the output. And on the right we have a NAND gate, which is just a AND gate with an inverter attached to the output. Okay, so let's look at the NOR gate first. Now, some background information. If you're not familiar with an OR gate outputs a logic 1 if any of your inputs are logic 1. So for inputs 0, 1, 1, 0, and 1, 1, the output's going to be 1. And for an input 0, 0, the output will be 0. Now, an OR gate is just an OR gate with inverted outputs, okay? So we're going to see that the NOR gate just has the flipped outputs. So if we label inputs X, Y, and output Z, for any input that has a logic 1 in it, we're going to output a 0. So for input 0, 1, we're going to output a 0. For input 1, 0, output a 0. And for input 1, 1, output a 0. Now, if we input 0, 0, our output's going to be logic 1 or high. So as you can see, we've essentially just flipped the outputs. Okay, so let's look at a CMOS circuit example. So I'm going to go through all of the possible inputs and verify that this is indeed mapping to a NOR gate. Okay, so if we input 0, 0, these two PMOS transistors are on, so VDD is connected to the gate of these two transistors, which then turns on this NMOS and connects VDD to our output, so we get a logic high or 1. Now if we input 0, 1, like so, this PMOS will be on, this PMOS will be off, this NMOS will be on, which connects ground to the gate of these two transistors, which turns on this PMOS, connecting our output Z to ground or 0. Now on the flip side, if we input 1, 0, this PMOS is on, this PMOS is off, this NMOS is on, which connects ground to the gate of these two transistors, turning the PMOS on, connecting Z to ground, giving us logic 0. Lastly, if we input 1, 1, these two PMOS transistors will be off, these two NMOSs will be on down here, again connecting ground to the gate of these two transistors, turning the PMOS on, giving us an output of 0. So as you can see, this maps directly to a NOR gate's characteristics. Now, a NAND gate. But first, in case you're not familiar with an AND gate outputs a 1 if all of your inputs are logic 1. Otherwise, it outputs a 0. So this is your truth table for an AND gate. And again, a NAND gate just flips these outputs. So if we label inputs as X, Y, and output Z, our NAND gate is going to output a 0 if and only if all of your inputs are 1. So for input 1, 1, our output's going to be 0. All other inputs are going to result in an output of 1, like so. Again, you'll notice we've just flipped the outputs from an AND, get our NAND gate logic. Okay, let's look at a CMOS example. Again, going to go through all of the possible inputs and just verify that, hey, this is indeed a NAND gate. Okay, so 0, 0. These two PMOSs are on, connecting VDD to these two gates, or the gate of these two transistors, rather, turning this NMOS on, which connects VDD to our output, giving us a 1 is our output. Now, if we input 0, 1, this PMOS is on, which again connects VDD to the gate of these two transistors, turning this NMOS on and connecting VDD to our output. Now on the flip side, if we input 1, 0, this PMOS is on, again connecting VDD to the gate of these two transistors, turning this NMOS on and connecting VDD to our output, giving us an output of 1. Now lastly, if we input 1, 1, these two PMOSs will be off, so there's no connection from VDD down here. These two NMOSs will be on, connecting ground to the gate of these two transistors, which turns this PMOS on and connects our Z to ground, giving us an output of 0. So again, you'll see how this maps directly to our NAND gate logic.